Hi everyone. So today we'll be going through this notebook on training an LLM for tool calling. We'll be discussing two main techniques, SFT, and we'll be comparing it with DPO, which is direct preference optimization. And we'll be parallelly training both of them and evaluating both of them to see how they compare against each other and how DPO can be useful. So to maintain the same comparison, we will use the exact same training data, the same evaluation data, and each method will train independently on the same base model. Finally, we'll also generate comparison reports to make a thorough comparison between the two techniques. And we'll also see how the model improves compared to the base model which we are fine tuning. So the training pipeline is the base model. We'll fine tune it with SFT, and the base model we'll also fine tune it with DPO, as I said. Now coming to installing the dependencies. So the main dependencies required are the TRL library, which is the transformer reinforcement learning library. It provides us with the SFT trainer and the DPO trainer, which we'll need for fine tuning the LLM. The PEFT library is the parameter efficient fine tuning library, which enables us to fine tune the model with LoRa, and so that we are fine tuning memory efficiently. And finally, the datasets and transformers library, which we'll use for loading and pre-processing the data, and also the accelerate library, which enables the distributed fine tuning and also mixed precision training. So as you can see, we have installed these libraries and we are ready to go. So now to actually use these libraries, we'll import these libraries, and we also import other Python standard libraries for file input output, regex parsing, and even timing information. We also import PyTorch libraries, and finally, as you can see, we have imported all of them, and we are ready to use these libraries actually in our code. Cool. So for configuration, so coming to actually defining the configurations for all the fine tuning. So we want to upfront define all these configs which we'll be using, so that we don't have to come back or hunt for these configurations. So we'll specify all of these configs in one place. So finally, as you can see, we have specified the output directory. The base model which we are going ahead with in this case is the Qwen 2.5 1.5 billion instruct model. So this model is a good balance between size and it has good capabilities. So we'll be going ahead with this and fine-tuning this in our experiments, all of them in this notebook. Finally, deciding the dataset sizes. So we are using training samples, 500 training samples and 50 training samples for evaluation. So we have come at this number because a larger training samples will require much more time for fine tuning, and since we are just experimenting, we'll go ahead with 500 for now, and we'll see how good the results we get. Finally, to enable or disable LoRa, we use the use LoRa config, and for mixed precision, we are using the BF16 config, which we have here. Specifying the LoRa configs, currently we are using LoRa of rank 16 and LoRa alpha of 32. So this controls the scaling factor for the LoRa. And finally, we are using a dropout of 0.05 during LoRa fine tuning. This is just different directories for the different outputs of the fine tuning experiments. And finally, we have set up all the configs and we are ready to go. So now coming to tool definitions. So we need to define the tool calls that we want the model to learn. These are the actions that the model will learn to invoke whenever necessary. So the format we are using uses special markers. So we are using the square brackets tool call whenever we want the model to actually make a tool call and use those tools. So finally, we want to define all the tools which we want the model to be able to use. So upfront, we are basically defining the tool call start tag which we want. These are markers that wrap the tool calls whenever the model is outputting a tool call. And the tool call end is the end tag. Finally, this is the registry for supported tools. So each registry is an entry and it has a dictionary. So the dictionary has a name key and a description key. The name key specifies the actual name of the tool call which the function needs to call, and the description is for the LLM to actually get an understanding of what the tool can be used for. So for example, supported tools, we can see get weather, the name is get weather, and description is basically it gets the current weather for a location. Get current weather gets current weather for a location, and so on. Calculate is basically evaluate any mathematical expression. And we have similar different number of tools for finance, communication, information, calculator, and general utility tools. So total we have supported, we are adding support for 20 tools currently. Now we are defining helper functions. So helper functions are basically just utility functions for data processing, model loading, and response parsing, which we'll need to use later. So we'll just upfront define all of these. So some data processing helpers. So we have some functions, for example, get tool from example. So this extracts the tool name used in a training example. So for example, if our training example has a particular tool, we'll extract the actual tool being used or called in that dataset example. So in this, we are just getting that example and searching for that function called tag, which we have, which the model generates, and actually return the actual tool name, which is in supported tools registry, which we just created. Similarly, this is a helper function for is no tool example. This is for actually checking if the conversation has a valid tool call being done or not. So this is just a check, true or false check, whether this example actually uses a tool call or not. And similarly, get tools from prompts. So this extracts the tools mentioned in an example system prompt. So any example will have a system prompt where all the tools are specified. So this gets us the tools, all the tools which are specified in the system prompt. So it finally returns us the tools, and we get the final tools in a particular example, which are being specified in the example's system prompt. So now, and finally, we have also format tools for prompt. So we are formatting the tool list to be included in the system prompt so that we can provide it in a structured, clear manner for every example of how we tell the model the available tools it can use. And finally, so as you can see, we are creating a clear structured format. So for tool in tools, dsc tool.get description. So we're getting the description of the tool and the name of the tool. And finally, we are appending to use a tool. We are specifying the name, the tool name, and the tool call, the description of it, and or any arguments which it takes. And if no tool is needed, respond normally. So this is constructing the actual prompt for the system, for the model, that if we all the available tools to it, and if no tool is needed, how it needs to respond normally without using a tool format. So now coming to helper functions for model loading and generation, we have simple functions for getting the LoRa config. So the LoRa config just returns us the actual LoRa config, and we specify it with the rank and alpha and dropouts, which we have specified in the beginning of the configs. And this just returns us the LoRa config. The load model and tokenizer. So this function specifically, load model, handles both base models and LoRa adapters. So it automatically detects if we are trying to load a LoRa adapter model or a base model, and returns us the particular model and the tokenizer. So as you can see, we are instantiating the tokenizer from auto tokenizer. And finally, we are also specifying the paired token if it is not specified in the tokenizer, and setting it to the EOS token. And finally, we are checking if the model path which has been specified to be loaded is a LoRa checkpoint, or is it the base model checkpoint. If it is a LoRa checkpoint, then we actually load the LoRa adapter. So we first load the base model, and finally we load it using the PEFT model from pre-trained, and we load the base model with the LoRa adapter checkpoint which the model path has. Else, if it is not a LoRa checkpoint, we just simply load directly the model from auto model for causal LLM from pre-trained and use the model path directly. This is the generate response helper function. So this is for actually generating the response from any base model. So this sets up the message template properly and actually generates the model responses by sampling. So directly coming into it, we have the messages. So we have the prompt which is going into it, and the role is specified as user. And we actually tokenize the text using the tokenizer, which we have just here instantiated. And finally, we apply the chat template to the messages so that it is properly into a proper format before it goes into the LLM for decoding. Finally, tokenize and move to model devices. So finally, we have the text and we are tokenized. So first we apply the chat template to the messages, and finally we apply the tokenizer to actually tokenize this text chat template to tokens. So finally, we get the actual inputs which we need to pass to the LLM. So finally, if we go into it, generate with sampling. So we have the model which we need to generate output from. So we do the model.generate function, pass in the inputs, and we specify some configs like the max new tokens which we wanted to generate, whether we want to do sampling and or greedy sampling, and finally the temperature, which controls the randomness in the final output of the model. After we have done getting the output from the model.generate function, we want to decode these new tokens which we have got. So, but we also want to only decode the output and not the input which had gone into the model. So finally, we do a tokenizer.decode on the outputs, and we slice it to not include the input ID shape. And finally, we get the response and we strip it down and return it. Now this function detect tool call is basically for detecting and parsing tool calls in a model response. So it supports two formats. So we have added supporting format like a tool call in square brackets where a tool call is happening. This is our target format, and we also have the tool call format as function call tags, which is in the source data set. This is how the data is present. So finally, this is for detecting whether the model actually made any tool call in its generated output. So we define these markers, and finally we are looking for these markers in the actual output response from the model. So we look for these patterns, and if there is a match, we extract the actual tool name which was called and actually parse the full JSON and load it. And finally, we return true if there was a tool call made, and the final tool call JSON is also passed after loading the JSON. Coming to data preparation. So converting this, we need to convert the source data format into suitable formats for SFT and DPO training. So currently the source format, we'll go through it, how it is formatted. And we use the same formats for both SFT and DPO training so that we have a fair comparison between both the methods. So we have some data format conversion functions. So for the SFT format, we want to convert to chat messages format. So it will be like a chat user and then assistant, then user. So it will be like a chat format. So the system message, the main system message will have the tool definitions. So we'll have all the tool definitions which are usable by the model. And finally, the user assistant message pairs are there, and tool calls are converted to our tool call format with the square brackets so that we can parse them properly. In the DPO format, we create actually preference pairs. So we have the input prompt, which is the user query with the tool context, and the chosen and the rejected responses. So the chosen are the correct responses which we get from the training data. The rejected responses are incorrect responses generated by the base model. So we'll go through exactly how this works. So coming to the actual function, converting it to SFT format. So we have the messages list, and we get the system prompt from the example and the chat. And we basically process the system message and convert any old format instructions to the new format. So instead of using the tool, we specify how to specify the tools in the system prompt. So it says to use a tool, it needs to use tool call start and tool call end and the name and the arguments, and it needs to specify that. So we are specifying to the model that this is how a tool call needs to be done. And finally, we are splitting the chat into role-based segments, so based on the user and assistant. And finally, we are parsing each turn from the user or the assistant and building a messages. We are building this messages list, which we initialized here, and building it with the user and role, the roles assigned properly to each segment, and finally returning that as the final result from the function to convert everything, convert one example of the dataset to an SFT format. Finally, coming to converting it to DPO format. So converting an example to DPO format is basically converting it to a prompt plus chosen response format. The rejected responses will be added later, but for now, so DPO requires pairs of prompt, chosen, and rejected results, rejected text, where chosen is the preferred correct response, which we ideally want the model to learn, and the rejected is the dispreferred or the incorrect response, which we don't want. So coming to the actual code, so the chat, we get the actual chat from the example, and finally we do the same thing. We extract the user message and the first assistant response. So coming to the data preparation part, so we want to convert the data set which we have into proper formats for the SFT and DPO training. So using the underlying data, so we want to ensure fair comparison. So we'll convert them into the same formats. But DPO requires us to create it in such a way we have a prompt and chosen and rejected categories. And SFT requires a system message with followed by user and assistant message pairs. And the tool calls are also converted to the format which we want. So we want it to be in a tool call a square bracket format. So coming to the actual function, converting it to SFT format. So we get the actual example from the dataset, and we get the system message and the actual chat from the example. So we build the system message. So the system message, we process the system message and convert the old form instruction to a new form where we specify how the model should use a tool. So we specify to use a tool, it needs to call the tool call start tag and actually specify the name and the arguments, and finally the tool call end tag. And finally, so this is added to the messages. Now actually the user assistant turns which are followed, we parse them and we get each segment from the chat for the user and assistant and the function response. We also define a function called replace function call, because we want to replace the actual function call tag with the tool call tag which we want to use. So we also specify that, and this basically just replaces that. Now this loop is just for going through each role and assigning the correct role and appending those to the messages list. So finally we'll have the messages starting with the system role, and finally each user, assistant, or the function tool. So function responses will have the role tool. So we'll have all of these roles properly defined and in the messages as a list of how the conversation is going ahead. Also, so if the current role is tool responses go back to the user role with special markers. The tool response, the actual result from the tool, is assigned to the role of the user, and we get those here. Now converting the format to DPO. So for DPO, we require pairs of prompt, chosen, and rejected pairs. So where the chosen is the preferred response from the model and the rejected is the dispreferred or the incorrect response. So this function extracts prompt and the chosen. So we do a similar thing. We do a user match and an assistant match. So we search for the user turn and the assistant turn in the chat from the example. And if so finally, if the user message, we get the user message and the assistant content, we check if the assistant content has any tool call. We have the same function which we defined above, the replace function call, to correct the format of the tool call. And finally, we convert chosen response to our format. So we use the assistant content and we convert the function call being happening in this to the format we want. And finally, we build the prompt with tool context. So we want to build the prompt which the final tools are being used in the example. So we use the previous functions which we defined, get tools for prompts. So this function extracts the tools mentioned in an example system prompts. And finally, once we have the tools which have been defined in the example, we can get the final prompt of being used using the format tools for prompt function, which we defined earlier. So this function uses format tool list into a string for inclusion in prompts. So basically this will actually properly tell the model how to use the given tools. So finally we'll get the prompt with the user query added to it. So we'll get the available tools and the user query, and this will give us the final assistant response. So finally we return the prompt, the chosen prompt, and whether it had a tool call or not in the assistant response. Now finally, to actually load this data, load the tool calling data set and use these functions to do our training finally. So we load the glef function calling dataset and filter to supported tools. So since we defined a list of supported tools which we want to train the model for, we'll filter the dataset for actually only using these tool calls and examples where these tool calls exist. So, and both the SFT and the DPO will be done on this filtered dataset. So this prepared shared dataset is preparing the training and the evaluation datasets from the glef function calling dataset. So this is just preparing the JSON files for the final data and checking if the data already exists. So we cache the data so that for faster reruns. Take what is the total amount of samples we want to actually fetch, and we only load those many. And we also load just 3x buffer for filtering, because since we are going to finally filter the dataset, we are just loading total 3 times the amount and then we'll filter it down. So finally we get the raw dataset, we get the tool calls which are being used. So as you can see, the tool name is fetched from get tool from example. So for each example we get the tool name, and if tool name is we have a tool name which is retrieved from this function, we append that to the filtered dataset. And if there is no tool example, then we actually also append that, because we also want cases where there is actually no tool call happening from the assistant side, but the LLM was told about tool calls. So finally we get the list, and as you can see, we build the final training sample of 500 samples as the config which we had decided, and the final eval samples. Now to perform the actual training, the SFT training, so we'll train the model to mimic the correct outputs directly. So the model learns from input and output pairs, and it trains with a standard cross entropy loss on the target tokens. So as you can see, now we'll go ahead into the code. So we have functions set up to convert the data, training data to chat message format for SFT. So how we go ahead with this is, we convert the training data as we discussed to the SFT format. So for each example, we do that and append it to the SFT data. Finally, we build this dataset from the dataset class, and finally we load the model, the base model, the Quen model which we discussed, into the SFT model along with the tokenizer which we want. Now to build the actual training configuration, we use SFT config class. We specify the number of epochs, the batch size, the gradient accumulation, the learning rate, and everything else in this config. And finally, we use the SFT trainer to actually train, to set off the training with this config. So once the training is done, so as you can see, we do the training, this completes, and we can see the training loss and the validation loss on this, and we save the checkpoint for further evaluation. Coming to DPO training, so direct preference optimization, it learns from preference pairs without a reward model. So we learn from the prompt, chosen, and rejected triplets. So we'll go ahead directly into how the code works. So as similar to SFT, we first convert the data to the DPO format, which we using the function which we initialized before. So now once we have the DPO extracted dataset, so we have extracted prompt chosen pairs, the number of these. So as you can see, if you come here, we extracted 500 prompt chosen pairs. And now, so for every item in the extracted prompt pair, we are also generating what the base model would say, which is usually the wrong format. So we want to make the model learn that this is not a preferred response. So these rejected responses are being generated now. So initially, using the function convert to DPO format, we generate the prompt and the chosen pairs, but we also want the rejected pairs, which we are generating now. So we generate the response from the base model and the base tokenizer. So finally, we get these rejected responses, and we only want to keep those samples where the chosen response and the rejected response are different meaningfully. Because if they are same, then already the model is working pretty good and it is responding the same. So it won't learn anything useful from those training samples. So finally, we create the DPO data, which is consisting of the prompt, the chosen prompt, and the rejected prompt, which we are picking from the base model. Now finally, we create the DPO dataset from this DPO data, and we specify the DPO config, which is the DPO out. So we specify the output directory, the beta, the KL penalty weight, the learning rate, and other configs. Finally, we create the trainer and we set off the training. Finally, we save this model to the checkpoint, and we are done with DPO training. So as you can see, the training loss is here, and we have saved the checkpoint. It took around 28 minutes to train the DPO model, and it took around 2 minutes for the SFT, which is pretty fast. Now coming to the actual evaluation. So we want to evaluate all three models, the base model, the SFT, and the DPO on the held out test set. So this will measure how well the model learned to actually use the tools correctly. So we measure multiple aspects of tool calling, tool name accuracy. So how accurately did the model correctly select the tool which needs to be used. Tool usage rate. So how often is the model actually calling tools in general when it should. And no tool accuracy. So how accurately is it avoiding using tools when it is not required. And finally, an overall accuracy combining, so it measures the combined correct behavior. So evaluate model, if we go into this, we basically have these metrics set up. So if it expected a tool, this example requires a tool call. So we set up the test case. So we are basically evaluating the model's tool calling performance on the test set in this function. It runs inference on all the test examples and calculates the accuracy metrics which we just discussed. So coming to finally the running the evaluation. So first we have set up the test cases. So the test cases from the evaluation data are set up with whether the tool call is expected, whether it should use a tool call, and what tool if it is expected to call a tool. And finally, we run the evaluation on all these test cases with the model in the eval mode. So if you can see tools prompt, format tools for prompt, build prompts. So we are basically again building the tools. We are building the prompt from the tools and finally getting the final format, which is the tools to be used and the user input prompt. Finally, we get the response generation and we are parsing through the generation to score it. So from the response, we are actually checking if it had a tool call and what is the tool call it actually used. So what is the tool it actually called. So this is finally we are getting if it expected a tool call and the tool name which was called. So finally, we get all of these metrics, the tool call metrics, the tool accuracy, the tool usage rate, and the no tool accuracy also, and we are finally printing them. So finally, we are just running evaluation for all these models and we get the results. So if you compare test cases, we had 50. So for the base model, it should use tool. So it should use a tool call 16 times and should not use a tool call 34 times. So the results for base is tool name accuracy is 31%. So it accurately is capturing 31%. And tool usage rate is 31%. No tool accuracy is 100%. So whenever it's not needed to require a tool call, it's always doing that, but that is expected from the base model. Now, if we evaluate the SFT trained model, we see that it is much better. Tool name accuracy is 87% and tool usage rate is 87%, and it is also avoiding the tools properly. Comparing it with finally the DPO, which is the tool name accuracy is 81%, 81% in tool usage, and finally the no tool is 100%. So now we have basically successfully trained two fine-tuned models using SFT and the DPO, and we can see that we are getting results and we can compare all these results across each other, and we can finally see how different fine-tuning methods compare with each other for the tool calling tasks in this case. And if you want to do an improvement analysis, so we calculate and display the improvement of each fine-tuned model on top of the base model. So we are basically checking the delta SFT. So these are just the difference parameters and how are each fine-tuned model comparing to the base model. And if we do a detailed error analysis, we can even check where did the model miss, where did it incorrectly call a tool, or did it correctly call a tool, and how many times did that. So if we see missing tool call in case of base model is 11 times, in case of SFT it is 2 times, in case of DPO it is 3 times. And similarly, we can get other metrics to see how where the model is doing better or where the model is doing worse. Yeah, I think that is all. Thank you.